Can you all hear me? Good. So I'm going to repeat the style I had, for the previous two lectures, although I don't see many students, right? So, so call on students, but they're rolling in. That's fine. So I want to continue the thread of thought, but I want to just review, right, the system. So the first motivation, we want to select communities because in communities, species interact and can thus perform functions that single species cannot do. So in this classic case, right, I mean, it's a classic in the sense of bioengineering, you have a helper manufacturer. The helper can degrade some waste, which I didn't do because it's in excess, right? Some waste, some cellulose waste, for example. And the helper manufacturer compete for some resource, like a nitrogen source, right? So helper would just degrade the waste and generate itself and some byproduct, like acetate. And this byproduct and the resource are then required by the manufacturer, M cells. And M cells, so basically a partition, it's kind of like a decision, right? Like the fraction FP is used to make the product we want, and the rest is used to make biomass. In fact, I want to emphasize like this kind of systems have been used in engineering, in bioproduction. So for example, the helper would degrade some cellulose and make, so for example, like tryptophan. Tryptophan is a very important molecule. And the tryptophan then is used by the M to make like sort of like, it's like modular, they call it modular, because you can have different M's that transform tryptophan to different compounds, right? So then the final product, right, is made. So, so the byproduct has no cost. So the important thing to keep in mind that we could discuss a lot is this cost, right? Because the more you invest in making a product which we want, the less fast you're going to grow. So we discussed the system and we went through the equations. And we went through the process of community selection, right? So let's see, hopefully, yes, exactly. So community selection, I don't actually have that. So community selection, the process is that you start with a fixed number, say, of communities, right? And we call it newborns. So newborns of lower, actually, I don't mind drawing it. So you started with newborns. And Sylvia also talked about that yesterday. So it's a small, like lower cell densities, right? And then you go through maturation. And this is artificially imposed, right? All the communities also, the boundary is artificially imposed. And then becomes adults. So adults have higher cell densities. So during this maturation, cells will divide and they will interact. They will make the product, right? So after you have adults, you will then rank them according to how much product they have produced. And you choose the top performing ones and then reproduce, right? Reproduce the different ways of reproduction. But so a very common way is you take you subsample, you do a sample of this and you put in new tubes, right? So you generate the newborns. And so this is like, so I call this parent generation, right? This is parent generation. And then the newborn, if they go back, it go to adults, right? They go to adults again. And then this is offspring, right? The offspring generation. Offspring generation, right? So when we realize there are many experimental variables, like the number of communities you choose, how much resource you put in, how long you wait, the mutation rate, and how many % of the adults you choose to reproduce, and species choice. So we went through all these, right? So we did discuss like the number of cells in newborns. They must be intermediate, right? They cannot be too low. If they're too low, then you could lose one species. If they're too high, it's a problem of possible cheaters. So I just want to, so today I actually found the figure. So I just want to say, right? So if we only allow, if we are only concerned about M cells and the cost, right? The cost can mutate. And so if we start with a large newborn size, what happens is that fraction of the cheaters would deterministically go up because if each each community would already have pre-existing cheaters in there, so they all take over. If you have small newborn size, at least you have variations. You have variations to select from, right? And so then we conclude it has small, but not too small. And the maturation time, the duration of this time, right? So we said, so this is short, the top is short, it's short, and the bottom is like the long, like it's, top is 6 generations, the bottom is 100 generations. If the generation is very long, then again, you have deterministic, right, cheater fixation. So then we know, we said it's short, but not too short. So today we'll continue this, right, like about how to design such experiments, right, so that you can have effective selection of communities. So we did, because there's so many experimental variables, and experimentally trying out these strategies is very costly. So we thought initially we should try to do simulations, simulate the experiments in different ways, and then compare them, right, and compare the performance. So then we start with 100 newborns. The total biomass is 100. So it's one, say like one biomass is equivalent to 1 cell, so it's about 100 cells. So H to M ratio is 1 to 1. And fix the resource so that we have the resource up to 10 to the 4th total biomass. So from 100 to 10 to the 4th, approximately how many generations the cells would go through. Those you know, those outspoken students, they're not even here. Yeah. So you have sufficient time for each doubling. No, I say, so initially it's 100, right? So suppose the maximum, I was asking you what's the maximum, right? So from 100 up to 10 to the 4th, right? So how many doublings, maximum doublings you can go through? Yeah, about exact 6 to 7, that's right, the 2 to the right 6, that's good. So then we have maturation, so about 6, just as we said. So mutation rate is chosen to be, it's realistic, but it's very high, right? And if we lower this, it just will take longer, right? So it's 0.002 mutation per cell per generation. And the 50% of these mutations will just so-called null mutants, right? So in the sense that they completely disrupt, right? They completely disrupt the production of the product, so pay 0 cost now. And then the other 50% increase or decrease the cost by a few percent. And so then during the growth, right, so during maturation, so each cells will grow because they have a resource and they release byproduct, they grow in length. And then the R and the B, the resource and the byproduct, is used by M to grow its biomass. And a fraction of it is used to make a product. So once the cell size has become, if it starts with 1, once it gets to the threshold of 2, it will divide into 2 cells. It's very just like E. coli growth is just like that. And then with some probability, death happens. And then mutation also happens with that, with that probability. And at the end, we rank them from low to high. And we'll choose the top 2. As a control, choose a random 2 to reproduce. Each give rise to 50 newborns. So we recover the 100 from the beginning. And again, total mass, we fix it to 100, right? But it's because we use this, how many people have seen this instrument? Yes, yeah. So, so for people who don't know, this is a pipette. So pipette, you can pipette like volumes, right? Like small volumes, say from like a couple of microliters to say 1 milliliters, right? So that is a liquid transferring thing. So you have culture, right? You basically just you put the plant down and you let go. It's like the doctor's syringe, right? It just comes up and then you can transfer to a new tube. So that's what we use all the time. So then it's a lower density because we only do a fraction of the volume, right? So into the fresh medium with the fixed resource. And so during this phase, right, the growth phase, right, it favors the fastest growers, right? Because during this maturation, yeah, in fact, I should have asked you, during maturation, what is favored, right? So they're the version that makes a lot of product or the version that makes very little product or grows fast. right? So the one that grows fast, right? But at this stage, we prefer the ones that makes more product and grows slower. So you have this conflict. So this is called individual level selection, the top one. And the bottom one is like community level selection. So it's the classic multi-level selection problem, like in biology. And in fact, if we think about this, it's everywhere in biology, right? Because for example, in our body, right, like the cancer cells would tend to grow faster, but at the cost of the host, right? But it will be selected against at the host level because the host just dies, right? So we see this kind of multi-level phenomenon very often. And so if we choose random two, right, what we saw that community function just very quickly go to zero. So why is that? That's right. There's no community level selection, only individual level selection. And the individual level selection will favor the fastest growing individuals that make no product. So that's why it quickly went. So if we choose the top two, we actually see it got better, right? So these three colors are three independent simulations. So it's never going to zero. They at least didn't decline. But the function didn't improve either. Right, and so why is that? So let's think about the three criteria. What are the three criteria that are essential for successful selection? Yes. Right. Yeah, that's very good. That's very good. Exactly, exactly. So in fact, if you choose more, I will show later, if you choose more, it will go up. But like a little bit, but the slide is at the end of the talk, right? So like but what are other possibilities? There are like differential survival. There's differential survival, right? Or what about inheritance, heritability? And what is inheritance? So how could you check whether community function has high or low heritability? Yeah, basically you're looking at the parent offspring similarity, right? But you can even the parent. So let's see. Whoops, what happened? So basically what we do is that we let the top half is parent generation, right? The bottom half is the offspring generation. So we are going to correlate. We're going to check the parent function against the offspring function, right? So this is parent function, like this one. These will give me parent functions. These will give me offspring functions, right? Because the functions are asked in this example in the adult stage. And we see that is it high or low? Is it impressive, the heritability? No, it's not. It doesn't even show any positive correlation, right? Okay, so that's not good. But we want to understand what's going on. Like, why is this, why this not going up? And here, there are two variables here, right? So we only allow two things to change. One's FP, is a cost, right? It's cost paid by manufacturer. And then the other one is because we are doing pipetting, right? So then even though the total biomass is fixed, the ratio can fluctuate. Right? Even if the parent is like 50-50, the offspring can be 40-60, right? Can be 30-70, something like that, right? So we call this phi, right? The phi is a fraction of manufacture. So basically it's a fraction biomass, a fraction biomass, from M, due to M, right? So it's phi M. So these are the two variables, low heritability. So community function, right? Because we saw yesterday these system of differential equations, right? So then the P, the product at time t, depends on parameters and the initial conditions, right? Everybody's with me, initial conditions, because that's how you solve the ODEs, right? Because it's initial value problem. Once you have initial conditions and the parameters, and then it's so parameters are phenotypes, right? Like the growth rate, the affinity for metabolites, the cost you pay, right? So on and so forth. So phenotypes are genotypes. So here, there's only one thing that's changing, right? FP, because we fix all the other parameters. And then the initial conditions, there's initial resource, initial total biomass, initial species ratio. So the resource we have fixed and the biomass too. So the only thing that's changing, it's this phi m that's changing. So there are only two variables. And we intentionally did this so that we can reduce dimension to, to a problem that we can visualize, right? Okay, so let's see the parent cycle, you have newborns, right? And then you go to adults and you produce newborns. And then you can ask, how does these two, right? How do the heritability of these two determinants, what I call determinants, right? So we look at the cost of the parent cycle and the cost of the offspring cycle. And we do this again, we have a different lineage, different color. And we see this very strong correlation. So is this a high or low heritability? High, that's right, because, yeah. And then we look at, so now it's heritable, but if we look at the composition of M, it's not. So that's a culprit, right? So it's not heritable. And then you can ask, well, these two, right? One's heritable, so one's heritable. So one's heritable. The other one's not, right? It's not heritable. So then we will see, well, how much do these contribute to the heritability of community function? Because each one can be more important than the other, right? So we'll look. So we'll look at, so we need to look at why is it not heritable? Why is this composition not heritable? Right, so it's because of ecological interactions, right? So let's see. So like we have this maturation time, and we covered yesterday, right? The helper will just grow exponentially, right? Because it doesn't have, we have enough resource, and there's excess waste, so it just grows. The manufacturer there will have a delay because it's waiting for the byproduct accumulation. But eventually they had to grow faster then they had to catch up with age to coexist, right? So then if they pay small costs, there's a potential, right? So in that sense, if it's a large cost, they always go extinct because they always grow slower. M always grows slower than H, so then M will go extinct, right? So let's see. So then if we start to say low value, cost low value, we start at different initial conditions of F, the phi, the fraction. You always go to this, the steady state value. Right, but if so we can plot it here. M's cost, if it's 0.1, it will be around, say, 0.65, 0.7-ish, right? So then we repeat this exercise. We say it's very, very high, it's always very low. And then whatever you start, it will just go to extinct. So here it's this dot. Right, exactly. So then you can repeat this again, like sample all these FP points, you get this. Right, so this is what we call the species composition attractor. So regardless of where you start in the newborn, you eventually get, if it's not the cycle, it will be, within a couple cycles. Very quickly, you will go to this attractor. But so what happens here is that suppose you have, because due to, initially say parent is different, right? So parent newborns start with different compositions. But because of this attractor, it will go to this value. And then you will do pipetting, and then the offspring has variations. But the average is this orange, the brown line, right? So if we correlate, right? So if we correlate so if we plot the newborn, the phi, the fraction M biomass in newborns of parent and newborns of offspring, what do you expect to see? expect to see this, right? Can somebody just explain to me why do you see this? Somebody who has not spoken. Yes. Yeah, it's because of this, right? See, if you look at this, initially there's a variation. It's just exactly this plot. There's variation here. So you have x-axis variation. But in the y-axis, if you look at this, it's just that it's the same. They all converge to this, right? So that's why you have the same, sort of like this brown line correspond to that brown line. So that's why. It's because of ecological interactions attracted these to this one fixed point, right? And then the offspring, so all the offspring newborns would have, right? So this green, oh, sorry. So see, if you start with green lineage, these are the green offsprings, right? And you start with this brown lineage. The brown offspring look just like the green offspring, despite the parents have different values. And that's why you have this. FP, no, FP we're trying to select. We're trying to select for FP, because cost, right? Because remember, FP there's the optimal FP. If we start with, say, a lower cost, we want to increase the cost so that they will make more product. Right, so here, so that is, so then this creates a restrictor, like a newborn restrictor. So whatever newborn you start with, it will quickly go to that. The FP changed much slower because it's going through selection. But the ecology is much faster. So basically movement, right? If you start, let me see, maybe I have an illustration, right? So, oh, sorry, I don't. So if you suppose like look at the laser point. If you start here, because FP moves very slowly, but within 1 or 2 cycles, you will already get here, right? So, so this is sort of like why there is it's sort of linked to why it's not heritable. Right? So regardless of the parent, how different the parents are, offspring are not correlated with the parent trait. So, so then you can say, well, like which one's contributing more, right? Because if community function is mainly determined by the heritable factor, then you will not, even if it's not heritable, if it's playing minor role, it doesn't matter, right? So we then see, right? So we see, oh yes.
I just had a quick clarification.
Yeah.
The phenotype is cost not a function of the phenotype? The phenotype being the amount of product produced?
Is what? It's sort of like if you have this system of differential equations, right? Eventually, it depends on so basically it's an initial value problem. So you will, you imagine you are simulating this, right? So then all these initial conditions are given. And then how this changes, right? Depends on those differential equations, the next step and the next step and so on and so forth. It's integrated over the entire maturation period of time.
What is?
The product, the final product, that's the thing. Community function we're selecting for. Product, it's the adult.
Right. So that is not the trait. You think you are calling
it's a trait of a community, right?
It's a trait of a community.
Right. That's right. So but it's determined. That's a very good point. It's determined by in this problem simplified to two things, two factors, two determinants. One is how much cost M is paying. If M pays no cost, there's no product.
Yeah.
Right. If M pays high cost equals 1, it doesn't grow. It goes extinct. Also, no product.
Okay.
Right, and also the fraction of M in the community, initial condition of the initial fraction of biomass. That's M. Because initially, if the whole tube is M, how much product will you get? If I give you a tube of M, 0, right? Because there's no helper. If I give you a tube of 0, no M, how much would you get? Nothing, right? Because there's no manufacturer, so you get a 0. So it's sort of like so basically there are two determinants, right? One is the fraction of biomass due to M in the newborn, in fact, right? Like because it's initial value problem, right? So of newborn. The other ones are like the cost. And you can see, well, a newborn has like different genotypes. You can just do the average cost.
Okay.
Those two would eventually determine. Yes, any other questions? That's actually good. We pause here. Very good. So if we see, so ideally, because this is the one we are selecting for, the genetic changes in the cost, right? But if we correlate this against community function, we see very little correlation. But in contrast, the fraction of M in newborn strongly influence the community function. So that's why we get confused, right? Because so in some other ways, like let me see, like, okay, so let me just do this in a more slow fashion, right? So suppose consider community one, right? There's a manufacturer, helper, they grow up like this. And this point, and the resource will drop, right? Because they're being consumed. And at this point, because we want to avoid the stationary phase, we stop, right? Because that's the end of maturation period. And then the product will accumulate like this. So now suppose, right, I start with a different community, I call the lucky community, right, with the dotted lines. So just slightly, H is higher, right? The H is higher, and of course M is lower because the total size is fixed. Right? So what happens is that H is initially higher, right, than the solid line, and this M is a little bit lower. And H can, because H is higher, M endures less lag, just slightly less lag. But that would allow M to grow to higher level than this. And because there are more M's, they make more products, right? So even if the F is the same, it's the same. So then the resource is depleted more, and the product is made more. So then we will think that this one is better than this one, even though the cost is identical. So it's like sort of like the noise during selection. It's something that gives you like a high value, but that high value is actually not heritable. So basically it's fooling you, right, into thinking it's very good, even though it's not very good. And so basically the community, the dotted community is lucky. I call it lucky, right? It appears very good just because, not because it's, it has a better genes, but rather because it had a lucky composition, initial composition. Any questions at this point? Okay, I'll try to ask more questions, right? Because there are very few questions come my way. Yes, go on. We don't know what. We do not know what is this byproduct that H is giving to M, and we don't know the details of the system, right? Oh, no, you know there's one byproduct. It's a state variable. We don't know. Do you know what it is? Because I was thinking, we are having this problem. One way I think we could deal with this is if we know what product exactly M is using, we don't need to, and if you want to select for like FP alone, this is creating noise. We can control the amount of byproduct we can maintain different tubes with just M and then select for M. Yeah, that's absolutely true. You're exactly right. But the point is that you don't know. Yeah, exactly, you don't know what the byproduct is. And plus, you actually, even if you know the byproduct, like the tryptophan, you don't want to just be adding tryptophan. You want to feed them with waste, right? Tryptophan is expensive. I'd rather just feed them with some cellulose and some microbes, let them grow. Get it? You're absolutely right. You just can use the byproduct, right? And see, right? If you know the byproduct, you could, right? But suppose we do not know. That's a very good point. Okay, so now we understand better. So basically, one possibility is, if you reduce the, yeah, go on.
I just, out of curiosity, how could you know? How can we figure out what is that byproduct?
How could you figure out what that byproduct is? So one possibility, also think about it, like I ask students, how could you figure out what that byproduct is? That's biology. Yeah, exactly. Do you hear what he said?
No.
Repeat.
Wow, okay.
It's not trivial.
It's not, yeah, it's not at all
It's not at all trivial.
straightforward,
Yeah.
okay. Can't you do like something like spectroscopy or something just to
Yeah,
figure
you
out?
could. The problem is that when you do like a mass spec, you see like many, many peaks,
Ah, okay.
and you don't know which one is.
Which one is
So
the
you
right
could
one?
do hardcore biochemistry, right? You like harvest a lot of like a lot of the supernatant. You do fractionation. That's really hardcore biochemistry. Fractionation, right? So basically, you elute the compounds in a column. So depending on the retention time, because these different compounds will have different retention time in the column, they will elute at different times. You collect fractions at different times. You ask, well, which fraction is the most important? And then maybe that fraction is still too complex. You subject them to second column, right? To finer, like to do finer fractionation. And until you get to relatively pure thing, and then you can just do mass spec to figure out what what compound that is. And even that is hard because if it's not protein or not peptide, small molecules like that, unless it's known kind of molecule, even to figure out the structure of it, it's not trivial. Right? So that is sort of like a biochemistry way. So he provided the genetic way, and the biochemistry way is like that. Yeah, yeah. So, so one possibility is to reduce fluctuations, right, in this species composition, right? So then we will basically reduce non-heritable variations. So then we reduce noise, so the signal becomes stronger, right? So it might work. So in that sense, the biology, we have this machine called a sorter, cell sorter. So basically it can, so sort of what it does, just like the facts I told you at the first lecture, but it does one more step. Right? So for each event that's like say green, it knows, okay, so if you say I want a 6-day green, 4-day red, it will deposit the first 6-day greens, and then the next, and then the 4-day reds into this tube. So you can control exactly how many cells you have. And if we do that, see the community function just improved. And what could be other sources of non-heritable variations in, community selection, right? During community selection. So this is one non-heritable variation, right? Fluctuations in initial composition of species. What are other like possible sources of Yeah. So we fix, sorry, I meant to say we fix species ratio by sorting a fixed biomass of H and M. So instead of letting them just, like if I pipette, I cannot control. If it's 50-50, it can be 60-40, it can be 40-60. But if I do sorting, I can ensure it's 50-50 because I'll pick the 50 of H and pick the 50 of M and then mix them. So it's guaranteed the 50-50. Yes, for every newborn, you reproduce. Oh, the ratio is naturally, it's just, okay, so the ratio is a parent. Whatever parent is, the offspring will. That's right. That's right. The first, the pipetting is, yeah, that's a very good point. The pipetting is the offspring ratio fluctuates around the parent. This one is exactly as a parent. That's right. It's a parent adult. That's right. Yeah. Of course, which could be different from parent newborn. Although if they're at the attractor, they're more or less, right, right, it don't change much. Yes. Yeah, but the thing is that you start, because the adult is already at this attractor, which is the same as the newborn, because the newborn is the same as this. Exactly, so then they're the same, exactly. So then we'll just stay around the attractor or the restrictor. What could be the other sources of non-heritable variations when you do community selection? This lady, the lady behind Sylvia. So the question is that, because we just saw example of non-heritable variations, right? Which is when you pipette, the species ratio will fluctuate around some level. But what are the other sources of, so during the selection, right? What are other sources of non-heritable variations you could encounter? So that there would, like, essentially as noise, you get the high community function, not because it's good, but rather because it's lucky. Maybe it's not so fair to ask theorists, right, that question. Are you a theorist? Okay, so who's experimentalist here? I don't think anybody will volunteer. And any experimental student here? No one. I don't believe that. But even theoretical, folks should be able to think about that. Yeah, very good. Very good. Environmental variations, right? Like the temperature change and so on and so forth. And also the measurement noise. When you measure something, you don't get exactly that, right? You can't, So for example, if a measurement noise is 0, we can get that. But when you measure community function, it's never like exactly what it is, right? Sometimes you can have more or less. But if it's low, you can see it's already kind of like a little bit struggling. And if it's really high, it doesn't even improve, right? So the so I will now, okay, so like, so before I go on, any more questions about this part? How much time? Yes, you have time. Yes, go on, yeah. That's right, you want to reduce them, exactly. Buffer, you can use buffer. Yeah. It's hard to control, yes. Say pH as example, even though buffer can control it, right? You can never be absolutely sure that they're exactly the same. But on the other hand, the pH, like, I think that's a very little bit special thing, because how could the pH change, right? It's because of the byproduct and so on and so forth, right? And maybe you don't want to actually control that. That could be one of it, because if it's some genetic change in H that makes it have more product, make the pH change, you probably don't want, because that is part of a heritable variation. So you cannot just completely change. You can, like a temperature, I think that's important, because there's no gene in there could possibly change the temperature, right? Or maybe there is, it's just not, not that likely, right? So it's most likely it's not heritable. But the measurement noise for sure is not heritable, right? So.
Does it matter if the heritability is due to epigenetics or genetics?
That's a very good question. So if it's epigenetic, right, if it's epigenetic, so the inheritance will be reduced, but there was some degree of inheritance. So I would say, I think it's not so useful. What do you think, Sylvia? Time scale, yeah. Yeah, in the extreme case, it's completely not useful, right? It's just like non-heritable. And in the other extreme, if it's extremely stable, then it's more like heritable. So but overall, I think it's not that stable, right? Like I would say it's probably not so good. Yeah, methylation can. Especially if this can be fixed. The initial epigenetic change somehow can be, right, can be made more permanent. But I don't know, but that's a hotly debated area in evolution. So I'm not sure. Yeah. No, we don't have temperature fluctuations. We only have 2 variables, right? But if I'm just saying for when you do experiments, but we can introduce a measurement noise very easily in simulations, right? So there's a more challenging case. It's a little bit related to what Sylvia yesterday talked about, right? If one grows faster than the other, and in her case, she wants some fixed color, right? In this case, we want coexistence of this, right? So suppose you have like, if H, so if we let H evolve, if it can evolve much faster, the M will go extinct. It doesn't matter what happens, it will go extinct. And the community function will be low. Excuse me. And so we want to see whether we can evolve growth restraint, right? It's very much like the Sylvia's case, right? Where can we grow, do this growth restraint? So again, if we try pipetting, we're comparing pipetting and cell sorting. So let's say the green line is upper bound, right? Evolutionary upper bound for the H's maximum growth rate, right? So if you do pipetting, you can see in 3 simulations, they all went to the very top, right? They all went to the upper bound. And as a result, the M just crashes down and the function is very low. But if we do cell sorting, it does not go to the upper bound anymore, right? It stabilizes at a level below upper bound. And as a result, M does not crash. And as a result, community function is high. So that's actually really important to control non-heritable variations. What did you say? No, I'm allowing H's maximum growth rate to also evolve. So now, before we control everything, right? But now we relax. So we allow H's maximum growth rate to evolve, right? And then the upper bound is 0.8. And at the same time, like we allow this, fluctuations of H and M, and then the cost. So now if we control, if we don't control non-heritable variations, if we do pipetting, you can see it fails, right? So H does not show growth restraint. It just grows to the fastest possible value. And as a result, M is outcompeted, and then there's no hope. But if you do very precisely, you prevent it, you eliminate this, so the ratio is still the parent ratio, right? But except you do not have these fluctuations in HM ratio. So in that case, H would evolve to be sub-maximal. So it has a potential to go to 0.8, but it's restrained now to below 0.8, and M does not go extinct, and community function is high. Yeah. Your community selection. Because if you have really high H, you have very low community function, you're selected against. Yeah, go ahead.
Sort of basic textbooks of ecology, we hear this competitive exclusion principle.
Yeah.
That if you have 2 species with same resource, then one should ultimately survive. So how is coexistence sort of going well with that?
Because in the classic case, they're not selecting at the community level. Okay. Right. But here, if I have multiple communities, due to variations, in some cases, M went extinct. I will select against this. And some of them didn't go extinct, and I'll keep them. So I'll keep enriching for change, so I'll allow them. Or I'm selecting for restrained H growth, right, such that they will coexist, because otherwise it will be selected against. So now we know, right, just so we're going back, we have two determinants. So one heritable, one's not heritable. We can actually plot, right? We can plot community function landscape. So the one axis is the cost, the other is the newborn M fraction, right? And these are so this will be high, the darker it is, the higher the community function is. So this is actually very smooth landscape. And if the mutate, if M, right, if the newborn has different M genotypes or M costs, we can just do average. This assumption is valid if the mutation is rare enough, right? Is small enough, or maturation time is short enough, and so on and so forth. So what happens here is that, whoops, is that here? Okay, so, and we can superimpose this newborn restrictor. So whatever, as we said, if the newborn, okay, maybe it's here, right? If a dot is here, so that's how you read it, right? You look down, okay, so the M's average cost is around, like, say, 0.15. And this newborn's phi M0 is around 0.55, right? And then what would it do? Like, so this is a newborn. Where would the adult be? Yeah, very good. I heard it, right, to go there. Because the change in this is very slow. And so from here, right, so the maturation, it favors cheaters, right, the faster growers. So what would that do? How would that influence the start? Where would it go? Where would during maturation, where would it go? Left or right? It should go left. That's right. It should go left. And during community selection, where would it go? Yeah, going the opposite direction, right? So this going opposite direction. So basically, it's a sort of like a type of war, right? Of this. So to see which wins. So if you use, so that's considered a case where you use pipetting. What happens is that we saw this already, right? It doesn't improve because of the low heritability. And so if we analyze more detailedly, right? So what happens is if you look at the contour, look at the more extreme case where it's like this, right? So I understand, right? It's almost like this region, right? So it's like this. So if in this region, if the newborn is in this region, then so what does that tell you? So changes in community function is due to what? Changes in what? In the heritable or the non-heritable determinant? In what? In the heritable determinant, exactly. So the change, because it's getting more dark, and this is due to changes in heritable determinant. So you should have high heritability. And if we think about just some random, right, like this is just I randomly do these communities. So initially, it's here, right, like it's average. The average is here. So if you look at the heritable determinant, right, this is the middle. And which one would you select out of these 8? Which one would you select? I would ask someday else. Maybe you again. Yes, you, yeah. Behind Sylvia. Which one would you select? That's very good. Yeah, that's very good. It's this one, right? So now you have this after. You have made max progress. Right. So now, if we do it that way, okay, so now changes in, so now what happens, right? Like the changes in community function is mainly due to what? I want somebody else to speak, like maybe that, you know, the girl sitting on the other side. So in this case, yeah, one of you, it doesn't matter, because the other one will be called next. So, so if you do this, in this case, the variation in community function is due to what? Due to louder. Right, due to variations in non-heritable determinant. And so this one is very good, right? So it's a low heritability. So if we do the 8 again, which one would you select? The other person, your neighbor. Which one will you select out of this? So remember, darker the line, the higher community function. So you want to go for the darkest one, right? Which one would you choose? The one on the top, exactly right, the one on the top, right? So the before, after the same, you're not making any improvements, right? So no progress. So how might we, you know, improve heritability? Right? So we learned the one method before, which is reduce non-heritable variation. But now we are learning a different, we are so okay, so this we just did. So it's a little bit redundant. We just did that, right? Oh yeah, so this is useful, right? So basically, if you do cell sorting, it's basically collapsing. Initially, you have these, right? So this one, just due to fluctuation, you have these, and this one is luckier. So you would tend to choose this one, even though they are equal, right? So by sorting, you're collapsing them onto this restrictor. And now you can see more clearly, if these two, you should choose this one, right? So the changes along the heritable line. And then also we go back to here, like, you know, so sort of like initially it's here, right? So if we go back to our problem, so if we look at the contour lines, it's like this. So these are the simulations, right? So we started with 100 of these, of like again, the newborns. So so again, I want to remind you, right? So for each dot, you look at the x-axis, it's the newborn cost, y-axis, it's the newborn m fraction. And wherever it sits, so when it becomes adult, what the community function will be, right? So how dark it is, the darker it is, the better it is, right? So in this case, intra-community selection will always lower FP, right? It's always would favor fast growers. So here we choose these two. These are the darkest one, right? And so what happens is that it's like this, and now it's here. So it's making some improvement during inter-community selection. So it's like this. So the net effect is that you're not making any movements. And it's this. So now suppose we consider this region, right? It's more vertical now, right? It's more vertical, even though like we blow up, it looks like this. So now we have this again, and we, intra-community selection always, right? It's the same. It would always lower the cost. And now we choose these two. We may have made a bigger improvement. And the total is like this now. So then, community function will actually improve. So then the question is, how would you move, right? Because the restrictor there, you're stuck here, but I want to go there, right? How would you do that? Yeah, how would you, do that so that you can shift it down to this region? And again, this y-axis is a fraction m in newborn. You can just add, you can just manipulate the newborn, right? You can manipulate the newborn composition, right? By, say, instead of purely going from the, as a parent composition, you actually take 70% from parent, for example, 30% age. So now you are forcing the m fraction to reduce. It's cumbersome experimentally, but do people see why that's the case? Basically, you're shifting the community from this not favorable region where it's not as perpendicular, right, to this region, which is perpendicular to the axis of heritable determinant. Any questions? And so essentially what it looks like is that when you do spiking, right, so you're forcing, because by substituting part of the biomass with pure H, and that's lowering the fraction of M, when you lower it, of course, it will go back up here again. So you have to do it every cycle, right? Every cycle you have to lower it so that you continue on this, so you basically continue to shift this down here. Yes. So there's a different way of doing that. So that way, even if you had, pipetting errors, it doesn't really matter anymore, right? Because it's a vertical. So changes in non-heritable determinant will not give you, it's all the same color. It will not give you the misleading reading. Yeah. Yeah. Yeah.
It's going to the yellow line, right?
Yeah.
And that is where I'm doing the community selection.
But yeah, but your initial composition has already changed. So by that time, you already have this, your community function would not be influenced by fluctuations in non-heritable variation.
But the community selection is happening after maturation time.
Yeah, but the product is accumulating throughout, right? From time 0, it starts to accumulate until T.
So you're saying community function is actually function of initial composition.
Initial and the parameters, the cost they are paying. That's right. And again, I want to emphasize, if it's completely, like a vertical, so this, you can see, right, this is more vertical than these. Like these are like not as vertical. So the vertical, it's like a quantitative argument, right? If it's more, like if it's strictly vertical here, then the community function, right? Like if you have exactly the same FP, but different to this non-heritable variation, you have identical community function. So basically, community function is complete readout of this. It's not influenced by the non-heritable variation at all. But in this region, it will be influenced a lot by that, right? In the extreme case, if it's parallel to, just like what we are saying, parallel to this, then the changes in community function is solely due to non-heritable, changes in non-heritable determinant. Then you'll be really confused, right? You'll keep picking big, the darkest one, but the darkest one is always the luckiest one. It's the offspring will not look any like the parent. Yeah, yes, you have a question, yes. Yeah, that, so I will go back to this. So actually, let me just go back, because he suggested a very good point, right? So top 2, it doesn't change, right? So given this case, I actually tell you, top 10 is better than top 2, right? But why is that? Yeah, but it's not like this. So it's true, but I think your answer is not precise enough, right? In the sense that, so okay, let me make the question more sharp. If you were to do self-sorting, do you think top 10 and top 2, would that make a difference? No, strength of sorting is perfect. Let's say it's perfect. I just want to sharpen the question, yes. That's right, that's right. So, so do people get what, I'm sure they didn't. So the discussion is that if in this experiment, if I chose top 10, if I pipette, if I choose top 10, it's better than choose top 2, because top 10 gives you more variation, but it's not quite precise enough. So I'm saying that if you don't have non-heritable variations, in fact, this top 1 is enough, or top 2, like 1 or 2 is enough, as long as you can generate enough offspring communities. Because if you don't have any non-heritable variations, right, then whoever is the best is indeed the best. But the minute you have non-heritable variations, right, some actually have good genes, but happen to be unlucky. And in this case, if you choose top 2, you're almost giving them a chance, right? Even though they are, they don't look good because they were unlucky, they still get to survive to the next generation. That's why top 10, no, if you do pipetting, top 10 will make a difference. That's right. But I will argue, you will see very soon, right? But even in this case, increasing heritability will give you a further boost. So it's not enough. So it's variation, it's, like variation and inheritance, right? These two sort of like you won't have to consider both, right? So you consider one aspect and inheritance another. Yes, your question. Is what?
Is influenced by environmental factors.
Yes. Well, here it's you can call it like the ratio. Do you call them environmental factor? The ratio of the species. M to H. Is that environmental? You can call it environmental. Like it's the environment of the community, which is the ratio of the. So I don't know what you mean by environment.
Like I was thinking if we could somehow maintain constant environment for all generations.
Yeah, constant environment. So that's what sorting is doing. Sorting is making the offspring ratio to be the same as the parent, right? The parent adult. Temperature, yes, of course, helping, fixing temperature, of course, will help, right? And the same, if you reduce the measurement error by repeated measurements, right? So you reduce measurement noise, that's also helpful, right? But I'm saying they're intrinsic factors. They cannot control by just doing this. It's sort of like fluctuations of this or where they sit on this landscape. Right, good. All right. What if a community function landscape cannot be visualized? So then what I propose that you could empirically determine community function heritability. How would you do that? Experimentally, right? How would you do that? You can empirically determine, right? You can try several different strategies, say which one has the highest heritability and use that one, right? Because for example, you don't know whether you should spike H or M, you can just try a bunch and compare those strategies, right? So how would you empirically, so suppose you cannot visualize a landscape, right? I mean, landscape, you can see, well, which one is, which one has the right shape, right? But if you cannot see, how could you empirically determine that? Do you want to give it a try? Yes. From definition, right? That's right. That's right, exactly. So if parent offspring has high correlation, right? So so basically what you say that you take the parent, right? You take the parent generation, and each one will reproduce several offsprings, and the offspring will become, an offspring adult. You compare the parent adult with offspring adult function. If they're correlated, if they're highly correlated, then it's heritable. So in this case, in simulations, right, so we have 6 heritable determinants. A lot of them all change. The cost, the maximum growth rate of H, the maximum growth rate of M, H's affinity for resource, M's affinity for resource, M's affinity for byproduct. And the 3 non-heritable determinants, right? So it's a newborn species composition, which we have just seen, newborn total biomass. So in fact, when you do pipetting, there's also biomass can fluctuate, right? Because if you're aiming for 100, you could get 90, you could get 110, right? So, and the measurement noise. So in this case, right, so we periodically quantify this heritability after different perturbation strategies, and then implement the perturbation strategy, conferring the highest heritability. And so if we choose top 2, just remind you, right, and reproduce by pipetting, we have this. We have this. So now going to that student, right? So if I do top 10, so now I'm going to show you top 10, like that. Right, so now if I do constant spiking, it's not much different, right? If I just try something. But if I look at different, if I, compare different strategies and see which one has the highest heritability and periodically switch to that highest heritability method, I get this. Right, so I think that is but all these are choosing top 10 from 100, and it's a pipetting. Yes. Oh yeah, so for every 100 cycles, right, I will just take some time, extra time to test, because it has been meandering, right, in the community landscape that I cannot see. So I want to make sure that they are in the region of, or like make sure the strategy is not outdated. So I would then do, so in fact, I think I have, so then I will, every 100 cycles, I will try these different strategies. No spiking, I put in 30% H, I replace the 30% with 30% pure H. or would replace with 30% pure M, or with 60% pure H, or 60% pure M. I see which one gives you highest heritability. That's to say when you correlate, when you regress a parent and the offspring functions, they have the highest slope, the highest positive slope. So I use that strategy. If I was using no spiking, and suddenly I see, well, 30% H spiking is better, I will switch to that strategy and continue for another 100 cycles. And then I retest. There are different ways of doing that. You can say, well, I will continue this method until progress is stalled. If it's not improving, then I can try this. We get a very similar result, right? So if we just continue to select, and once community function does not improve, we're going to check heritability and switch to the one with a higher heritability. So then we have this. Yeah, so it's a switching between, it's whichever is the best. We take that strategy. Every 100 cycles, we evaluate. Yes.
The same ratio as the parent itself. So why is there a need to try out multiple strategies?
Because I do not know, because in this case, all these things are changing. Because in the lower, in the two-dimensional space, I can visualize landscape, but in the higher dimension, I cannot see it anymore, right? I will not know how much I should spike, right? So this is just a trial. You can do like different, you can do like, say, different types, right? You could say, well, more resource or less resource. You can do all sorts of perturbation, but whatever way, different ways, you ask which one gives you the highest heritability. Okay, so I'm almost done, but that's good. That's very good. So summary, right? So large non-heritable variations, right, in community function can arise during community reproduction, just via routine experimental steps, like pipetting. So these large non-heritable variations can interfere with selection. So reducing these variations, right, would allow costly community function to improve. And we talked about the two strategies. One is suppressing variations in non-heritable determinants, right? For example, in cell pipetting, you do sorting, but that's very expensive. Reduce measurement noise, right? Or you can shift the attractor to a region with higher heritability, right? It's like the landscape at which your heritability is high rather than low. And also I want to say that, so this is the realization I had, right? So like math modeling can be so useful in experimental design. So actually now my lab has like predominantly theorists. so I've completely switched the form, mainly like all exclusively experimental, right? To sort of like let people do whatever they want, right? So like this project really made me appreciate, right, the importance of quantitative thinking. So I still want to make an announcement about the swimming, So yesterday what happened was like 6 boys showed up early, because they showed up early, they bought all the caps, they went in the pool, and the 6 girls showed up later, and they had nothing, right? Basically, they had no caps to buy. So I suggest the following, but some of the people are not here, right? So maybe you can, tell them. So what I suggest is the following. All the people who want to swim come, and we have 6 caps, right? So 3 boys go in, and the 3 girls can use the 3 caps. And the swimming suit, right? We can borrow from Sylvia, we can buy some. And then the second batch, so it would be 2 batches. So one batch would be at 6:30, right? 6:30 to 7:15. The other batch was 7:15 to 8, right? So then that way, like we optimize, right? We optimize number of people who can learn swimming, right? It's like game, right? It's a game we play.
Battle of sexes.
What did you say?
Battle of sexes.
That's right. Right, so does that make sense? So if you see your friends who want to know but they're not here, maybe they're too scared of my questioning. They don't even show up, which is counterproductive. Maybe yesterday's was too intimidating, right? So tell them that, right? So see you at the pool. But so I still have a few minutes. So I'm going to ask some questions now, right? Yes.
I don't know whether this question makes sense, but I was thinking, can heritability itself be seen as a trait?
It is a trait of the community. Right? Would you like, yeah.
That was the idea of
Yeah.
the model yesterday, that we evolve
That's right.
Heritability usually is more like a statistical concept.
That's right. It's like slope of the regression. It's a statistical, yes.
I was thinking even at individual level, can whether some property is
The cost is all the phenotypes, right? There's a determined by genes, the values that change. That is,
there.
Yeah.
Yes.
yes.
So among the non-heritable factors, you mentioned measurement noise. So what exactly do you mean by measurement noise?
Oh, measurement noise. For example, I looked at the tube to measure how purple it is. Right? Even though the real value is 100, my meter could tell me it's 105, 95, or something like that. Measurement noise, yes. So if there are no more questions, I'm going to ask you questions. Okay, good.
How stable are these communities? Because we want to actually apply this, say, in the industry or for, if you want to apply this in the real world, we also need to ensure that the, I think because individual selection will act in the opposite direction. So is the, and also in yesterday's simulations, we saw that if you remove community level selection, it goes back. So is there a way to prevent that?
Yeah, so did you hear the question? So is there a way to prevent, how stable is it? Right, because you need to apply constant like selection on it. Right, otherwise it will decline. There's a way of preventing this from happening. So what do you think? How would you answer the question? Do you have an answer? Is he correct? Does that make sense? It's not stable. Do you agree with him? Yes, you agree. That's true. It is because it's costly to individuals. So it is costly, right? So it is not stable. But so industry, I would suggest you could always freeze it, right? So you start a batch, you do this, right? Because of course during this maturation, it was because you selected for it, right? But then you cannot keep doing, right? So like you always go back to freezer to get that the strain of the right genotype. I would suggest, right? So, yeah.
Also, is there a way to, ensure that if we can visualize the landscape, that it can select it where it goes to a minimum? Does that ever happen where, the community function is at a minimum, and mutation or individual selection either direction will not push it out of it?
So repeat your question.
My question is it possible, let's say we can visualize a
You
complex
can or
landscape.
cannot.
Can.
You can visualize landscape and then
We find a minimum.
minimum of what?
Minimum with respect to community function.
Why do you want to find the minimum of community function? Because I want to maximize. A maximum, right.
Maximum, and it's also
Yes.
it's local, like in the sense that
Yeah.
if you move in either direction, it
Yeah.
doesn't change as much.
I see. So you want something that if you move a little bit, you're still going back to the maximum, right? You want the maximum to be stable, to be stable. If your attractor is near, it goes through, because the attractor I marked, if it goes through the maximum, right, then it's more stable, because at least composition is around that region, right? So that's the solution, because the landscape, right? Like, let me see. I don't know how many landscapes, how many do I have to go? Oh yeah, like that, right? So the maximum is here right now. Here, right? Like the top of the hill here. If your attractor happens to like coincide with the maximum, then if you are at the right, if you have reached the peak, then I would say, still like it's always intra-community selection, but I would say it's more stable because your community function, if your steady state composition is near that maximum. Yeah, but otherwise there's always pressure from intra-community selection if it's costly, right? Yeah, Sylvia.
Yeah, what if you had other parameters that can evolve? Then perhaps we could move that line.
Yeah.
Here you just have one parameter that evolves.
Yeah. Yeah.
But then you want to optimize something that depends on two variables.
That's right. That's right.
Like two parameters.
That's right. That's right. Just like in your case, right? The optimum ratio at which, right? So it's like related to Sylvia's talk yesterday. She wanted some colors, basically ratio, right, of the two. And you want the ratio to be wherever that is. So it's like, it's exactly.
With the difference that we selected for the final color, whereas you are integrating all the.
That's right, that's right, that's right, that's right. But the final color is determined by the initial color. So I can translate the final color to the initial color. That's right, yeah. Yeah.
Related to what he asked.
Yeah.
You're saying like, is the community stable because if we leave it, it will go back.
Yeah.
So the answer to that was after we do the selection, what community will get, you freeze that. So what
I,
is the answer? So what was the answer to his question that after we do all this selection,
Yeah.
we get a good community,
Yeah.
the high community function. Now, if we let that community grow or further,
no selection, right? Like no more community selection.
so it will go back. And what is the answer to that? What solution to that problem?
So I'm just saying that, to counter this costly, right? This costly trait, I would just freeze them at minus 80 degrees, so it will not evolve. I go back to the.
If we say we want to so if we want to use that, so somewhere some waste leak happened, we want to release this our super bacteria to clean that stuff up. That might not work, right? Because the moment we release it, the manufacturers are being selected to grow faster and produce less of the product.
But not, yeah, exactly. But I know I'm safe during the maturation time, right? Because whatever it happens during maturation, because that's how I selected them. So during maturation time, right? Because of course, if your time is much longer than maturation time, of course that is true.
Maturation time, we know that they will work.
Yeah.
After that, we don't.
Yeah, that we do not know exactly. I would say, but I would say from Sylvia's work, depending on the mutation rate, depending on the selection advantage, there are also fancy ways to do that, right? So industry, they have ones that couple the making of something, the product, to self-fitness. So somehow, if you don't make it, you release something to kill yourself or something like so. But even there, that can be evolutionarily broken. Yeah, yeah, but that can be evolutionarily broken as well, right? You break the suicidal program, but at least it's slower. It will be slower, yes. Yes, Sylvia.
I had a question, comment. So this looks very much like, Evo Devo kind of thinking. Like you have a newborn, you have an adult, and when people consider the evolution of development, they usually tend to focus on some later stage of development to take into account that there is some kind of canalization.
That's right.
Compensation of newborn random variation. So you have much more
That's right.
variability in newborns than
Yeah.
you have in adults. So do you have an opinion whether, what is best to do? Because could one just focus on adults and sort of, so what is the use of actually looking in detail newborns?
So newborn, because of I think it's for differential equations, right? Because these are the initial conditions that I care about. And also if mutations arise during this process. So we feel that, so for me, it's easier to think about the newborn because like in the newborn stage, yeah, because of initial conditions. But of course, you can say the final stage always reflects. You can always do a map, like what you guys did, right? The final against initial. So from this, the two are linked through the differential equations, right? That's right. Exactly. Yeah. And also, like experimentally, you can manipulate the initial condition easier. That's another reason. But as you for like, like in your case, yes, like for example, you want to say, despite the initial ratio fluctuation, you evolve the attractor basically, right? You evolve the attractor in adult state so that they're really stable. And then that's certainly, that is certainly like a very interesting, very interesting way of looking at, one aspect of the problem. But for us, I'm more thinking like, how would you, because adult stage is too late for me to manipulate. I want to manipulate in the newborn stage. So that is what it is. Yes.
Hello. Yeah. You've spoken of community level selection.
Yeah.
in my head, whenever I think of community level selection, the same way I think of individual level selection, I think of the two competing units are being discussed are that. So individual level selection is two individuals competing.
That's right.
But here, two communities don't really compete. They are separate communities, sort of having their own game, and then they're sort of evolving separately, and then you sort of see where they go. So, what the selection is still individual level selection within a community, right? Which is
It's a multi-level selection, right? You both have individual, you're right, during maturation it's individual level selection. But at the final stage, I will pick the darker or the more, purple, whatever, community at that moment. So that's why I call it artificial. I, as experimentalist, choose.
right. But let's say the things that you choose, there are a lot of non-heritable qualities which are different between these communities.
Yeah.
But two competing communities essentially should have the same non-heritable states, right?
No, not necessarily. Because, for example, if I do like measurement error, right? It's like, for example, if true value is both 100, right? So for this one, it's like 100. So for example, like I read both up to be 100, but in reality, one's only 80, right? The other one's 120. They're different. But to me, when I read them, I thought they were the same. So that's a non-heritable variations, right?
So like the community space
Yeah.
ends up looking similar to the communities which were able to produce the most product in the end, right?
Not necessarily, unless, if you don't have non-heritable variations, yes, that is.
So no,
Or
so
if you, yeah.
so like when we do like agent-based simulations, when individuals are being selected, the individual's fitness is what is used in order to reproduce the next population.
right.
So when you are doing this, you pick communities which have the highest amount of product because
Yes.
that is sort of the fitness of that particular
Yeah.
community.
Yeah,
Right?
that is the artificially imposed criterion for community
Right.
fitness. Yeah.
So when two of these communities which have the exact same product compete, and compared to say another which comes in with a separate setup competing with these same, so it's they would be stable when this new individual is not able to create any more product when interacting with these communities, right? But there is no interaction between these two communities. You never set that up, right? Like two communities never interact. So
Except that they compete for by selection, right? In that sense.
right.
But otherwise, they don't in this case because there's no migration. One could introduce migration.
Yes. Okay, so it's like I can only choose 100 communities to go in the next population.
It's not expanding, right?
Either one community reproduces or the other. But they're competing for being represented in the next generation.
And since drift is still a thing because these are finite populations, and like you mentioned that there could be some communities which start off lucky, right?
Yes.
Right? So why won't they just sort of sweep this community population?
They won't sweep in the sense that because the next generation, they won't be lucky. They may not be lucky.
Because they started with a non-heritable lucky
That's
space.
right. That's right. That's right.
Okay, thank you.
Right.